Hello everyone, I'm Dr. Sri Banerjee, epidemiologist, biostatistician, faculty member, and in this segment I'm going to be going over some of the basic components of a meta-analysis. Now, the meta-analysis in SPSS, there's not too many features as some of the more popular packages such as Revman. Revman is actually something that was created by Cochrane Review. And can be easily accessed in a Google search. So I recommend you start familiarizing yourself with this data set, with this program. Now let's take a look at let's take a look at some of the meta-analysis that you can complete here. And a limitation of this meta-analysis, just to give you some context, is that instead of, well, first of all, usually you're looking for interventional studies where you have pre-exposure and post-exposure. So if you're not familiar with randomized clinical trials or clinical trials themselves, the way to understand them is that usually, for instance, you have some sort of condition, and then you treat that by a medication. For instance, you could look at autoimmune diseases such as rheumatoid arthritis. If you treat this with corticosteroids, then what is the outcome? How many people have successful treatment, whereas how many people fail in their treatment? So you want to see the number of success and failure in the exposure group, and then number of successes and failures in the outcome group, and that's how you would kind of conduct this. Now, in this case, we're not going to go into additional research papers and try to mine for numbers. You were able to determine this from another assignment that you did in a previous week. However, this is very important to be able to mine numbers just beyond the scope of this lecture. So this is a standard data set, a sample data set that I created, and you can see the initial number of success in group 1 is 350. And then group 2, once they have been exposed, how many people are successfully treated and how many people had a failure. And so, as you can see, there's actually deleterious or harmful effect of the exposure. Now, that may be counterintuitive for many of you, because typically when you're thinking about a treatment, you think you're trying to improve. However, in ecological studies or environmental health studies, the exposure is typically some sort of environmental factor, such as endocrine disruptors or exposure to plastics. And so you're not really looking at success versus failure in treatment. You're more looking at the outcome of exposure to understand what is the individuals that are having the symptoms still, whereas individuals are not. So you can kind of understand success as people that have been that is truly not a success, just that these individuals are seeing side effects. So one way to understand this is individuals that have hypertension initially, and versus that upon follow-up you have exposure. You look at the number of cases that have hypertension after being exposed to endocrine disruptors. Practically speaking, and I'm going to go into the actual analysis, practically speaking, you cannot ethically expose people to endocrine disruptors to see how they behave. In an ideal situation, in a randomized controlled clinical trial, you should be able to expose people. However, ethically, that is not really doable. So let's go into analysis. These are the numbers that you start off with, and let's go into analysis. And again, this is you can use the continuous outcome, and there's two choices: raw data or pre-calculated effect size. We're not going to do raw data. We're not going to use continuous because none of these are continuous. So you can go into the raw data here, and then what I'm gonna do is drag these over to the variable so that you can kind of see the process of how this is happening. And we can change the success and failure to diabetes. So the treatment group, the success for treatment group can be found right here, the treatment group, and you can kind of carry that over, and then for the control group, success failure, you can drag that here. And here's the success. And let's drag that again. And then in group 1, the number of failure. So treatment group, success versus failure. Control group, success versus failure. And so the treatment group would be the group that got exposed, in this situation, got exposed to endocrine disruptors. And then control group is those that weren't exposed to endocrine disruptors. How is there? What is the impact? So success versus failure would be diabetes versus no diabetes. And again, there might be some discussion about where the success is versus the failure. And so sometimes you can make the argument that success means that these individuals develop the pathology or develop diabetes more so than people that did not. You can do a retrospective cohort study. However, in this situation, we're assuming that this is like a clinical trial, and treatment group would be people that are exposed to endocrine disruptors. So let's take a look at some of these menu items over here. There's a lot of different things that you can actually include in here. Let's cancel that. The analysis you can complete, and here's the variable names, and you can do a subgroup analysis where you're looking at the, for instance, males versus females, or some of the other areas. So let's select continue here, and we don't have that in this situation. You can go to print. There's some, for instance, test of homogeneity, heterogeneity measures, effect size. Here's the effect size of studies. And then take a look at this plot, and this is what is important. I think a lot of these show many sorts of ways to understand this. Now, the forest plot demonstrates the types of odds ratio and 95% confidence interval that is pertaining to this. So the way to calculate and the way to select and be able to see this forest plot is by selecting the forest plot here, and then the funnel plot is also very important. So the funnel plot is over here, and that can test for some important aspects. So just to continue on, the funnel plot is actually important because it assesses for publication bias. So what you have is this is measuring precision and the effect size based on the precision, and I'm going to explain this a little bit more in a moment once we run this data set here. So then I wouldn't worry about the bubble plot, the Galbraith plot, or the lab plot. I would just do forest plot and funnel plot. And remember, this is how you select that, and displaying columns, effect size, standard error, confidence interval limits, p-value weight. So you have, you can select continue, and then make sure you have your study ID in here. And remember, the study ID is not the same thing as study. Select OK. And if you take a look at this funnel plot, this is called a funnel plot, and this is how this looks. And let me pull up the other output and try to interpret some of this. And you're not responsible for looking at a lot of this. Just understanding, is there a publication bias going on? And indeed there is, because this is the overall observed studies effect size, and these are each publication, and some of these publications are outside, and so there is some publication bias going on. Now let's take a look at and again, this is a funnel plot, not a forest plot. Now if we take a look at a forest plot, as you can see, each of these, now these represent each study. So the error here, log odds ratio, all of these are mapped kind of right here. And here's the x-axis, and right here you'll see there's some that are above the x-axis and some below. So this is just mapped out, and this is a composite odds ratio of all of the odds ratio that have been formulated throughout this study. So the basic elements that are important to remember is that in a meta-analysis, not only are you looking at a composite of multiple studies, you're using studies that are already there to understand a composite study, as if you were completing one in terms of as you were completing one that was one study as a composite of many. This is why some people say that the meta-analysis is actually the gold standard, and even more superior to a randomized controlled trial, the level of evidence, as they call it. So there's additional measures that you can take a look at. Now that we have explored the forest plot and the funnel plot, it is important to look at some of the statistics to determine homogeneity versus heterogeneity. So the null hypothesis for this test is that there is homogeneity between studies, and so there is reason to be able to calculate and conduct a meta-analysis. However, when you reject the null, that means there is heterogeneity, and that means that some of the results might be questionable. Another measure that is more recently used for homogeneity versus heterogeneity is I-squared, and there's different ways to. So I-squared is another way of measuring this. Now there's not a significance test. However, anything over 50% means that there's heterogeneity going on. So as you can see, homogeneity versus heterogeneity is something that is important to explore and determine. These are the main measures that you want to be looking at in a meta-analysis. Again, if you're trying to you apply this to an environmental health study, then you want to be able to take a look at the exposure and what are the cases of, for instance, diabetes before versus what are the cases of diabetes after exposure of um, endocrine disruptors. I hope this has made some sense. Thank you for listening.